So dear students, today I am going to start a new topic of mathematical physics, that is Fourier series. Okay, so we have completed two topics of mathematical physics. One is single and multivariable calculus and another one is vector calculus. So if you want to complete the course on mathematical physics for IIT JAM, you can go to my playlist and you can see all the videos. Okay, so I have completed till now just two topics of mathematical physics, but I will complete all the topics of mathematical physics. Okay, at least mathematical physics before your exam. But if time allows, then I will go to the next topics that we have already started, that is quantum mechanics and electricity and magnetism or electromagnetic theory. Okay, so this class is the introduction class of Fourier series. Okay, so let me start this topic of Fourier series. Okay, so before going to the details analysis of Fourier series or the mathematical analysis of Fourier series, you have to understand why we need to know about the Fourier series, why physicists need Fourier series, this mathematical tool, why we need. Okay, and before Fourier series we have discussed one kind of series also, that is power series. Okay, if you have a course on infinite series of power series, then you know some function can be expanded in terms of some power of x, like e to the power x, sin x, cos x. These kinds of functions can be expanded by using Taylor series expansion, by using Maclaurin series. So these are basically the power series. Okay, and here I am going to discuss another kind of series that is known as Fourier series. Okay, so let me first give you a little introduction that why we need actually this kinds of series. If you talk about power series or if you talk about Fourier series, why physicists needs this kind of series. Okay, so there is some benefit of knowing these kinds of series in very physical situations. And one of the most important physical situation I am going to tell you, and I am going to give you that how this equation can be used in power series, and by using power series how this equation can be solved, and why we need Fourier series. I will tell you from there. Okay, so let me tell you a very common phenomena in physics. Everywhere in nature this phenomena is arise, that is vibration, or you can say oscillations, wave, vibration. These kinds of things in physics arises many times. Okay, a very simple situation of this is simple harmonic motion or a simple pendulum, you can say, because everything you can see in matter, from matter or in our galaxy there is a periodic motion everywhere. Okay, to a smallest particle to galaxy. Okay, and in matter there is some atoms, and the atoms are vibrating in about their mean position. So everywhere you can see this vibration, and the differential equation corresponding to vibration, I can give you the differential equation corresponding to a simple pendulum. If a pendulum is like this, so let me suppose that there is a simple pendulum which is hanging vertically, and if its angular position or its amplitude is theta, suppose if this is theta, then a differential equation can be set for this mass small m, and the differential equation, let me give you directly the differential equation, because you know this kinds of thing, we don't need to prove it here. So the differential equation for this kinds of problems is d2 theta dt2, okay, plus g by L into sin theta equal to 0. This is the general equation. Okay, this is the general equation, and we have taken this g by L as omega square, and if theta is very small, we can take this sin theta as theta, etc. We know it from our discussion in physics. Okay, but this is the differential equation that you cannot solve by using your tools, as you know in your differential equation. You cannot solve this differential equation analytically, the rules that you know in your differential equation chapter. Okay, because this sin theta is arise here. Okay, so you cannot solve this kinds of equation. So to solve this kinds of equation, we need to expand this sin theta in terms of power series. Okay, so if you know the Taylor series expression of sin theta, then you can write this equation in this way also, that is d2 theta dt2 plus g by L into theta minus theta cube by 3, okay, factorial 3 plus theta to the power 5 by factorial 5, and dot dot. This is the power series expansion of sin theta, and that is equal to 0. Okay, now you can write this equation in terms of theta, but here this is in terms of sin theta, so you cannot solve this equation, but you can solve this equation by proper approximation. According to the physical situation, you can take up to any number of term. Okay, sometimes in very simple case, for simple pendulum where theta is very small, its amplitude is very small, then we will take up to this term. Okay, and we know the differential equation for simple pendulum like this: d2 theta dt2 plus g by L into theta equal to 0, and this L is the length of this string and g gravitational acceleration, you know, and theta is the amplitude at that time. So this is the differential equation for simple harmonic oscillation, and you can easily solve theta from here. As theta is very small, so these terms can be neglected and you can take up to this term, and this is the differential equation for this. But if you want to take approximation up to this term, okay, for large amplitude sometimes it is taken that up to this term, this theta cube term, okay, sometime up to this term we like to take. Okay, so if you know from your physics, from your simple harmonic motion, that the time period from here we can determine the time period t is equal to 2 pi root over L by g, and if you solve this equation you will get the time period t is equal to 2 pi root over L by g into 1 plus theta 0 square by 16, where theta 0 is the maximum amplitude. Theta 0 is the maximum amplitude. So these kinds of problems can be solved only by using the power series expansion of sin theta. Okay, and according to some condition, some property of this function, any function you cannot expand any function in terms of power series. So there is some rules, obviously there is some property of this function, and only that kinds of function you can write in terms of power series. I will tell you later. And this is the requirement. Actually I just want to tell you what is the requirement of this expansion of power series in physics. Sometimes you will see this kinds of equation in radioactive decay. Okay, when you will study about this radioactivity, that is nuclear physics, you will see this kinds of equation also, that radioactive decay. Okay, and in radioactive decay you can find this kinds of equation: n is equal to n0 e to the power minus lambda t. Okay, and sometimes physicists like to expand this e to the power minus lambda t in terms of power series, and you know the power series of e to the power minus lambda t is n0 into 1 plus x, that is here minus lambda t, plus x square by factorial 2, that is minus lambda 2 whole square by factorial 2, plus dot dot. Okay, so sometimes this kinds of power series expansion is also needed in physics. Okay, so you can see the application of Fourier power series in physics in various situations. This may be arise. Okay, now let me tell you when Fourier series will appear. Then I will tell you what is the drawback of this series and why all problems cannot be solved by this kinds of series. Why we need Fourier series, I will tell you. But let me first tell you why this kinds of series is arise. Okay, so you can, if you want to get the solution of this equation, then you can understand. Okay, so this is a equation of simple harmonic motion. Okay, differential equation of simple harmonic motion. So instead of theta, if you choose x, okay, so let me suppose that a particle is vibrating along x-axis, okay, and its anytime position is x, then this theta can be replaced by x in that case, and this g by L can be replaced by omega square here, and that omega square is sometimes k by m also. You know, this is the discussion of actually simple pendulum or simple harmonic motion. I think you have studied this thing in your 10+2 level. Okay, so what is the differential equation in that case? This differential equation can be written in that case this like this. Okay, d2x, or you can write it as y also if you want. Okay, so you can write it in terms of y also. So in that case you will have d2y, okay, dt2 plus omega square y equal to 0. We will get this kind of differential equation instead of this. Okay, and if you know the solution of this differential equation, you can see there are various kinds of solutions of this equation, but the solutions are mainly in terms of sine and cosine. Okay, and instead of t, if you use the variable x, so let me use the variable x instead of t, so you will get this kinds of equation. Then you can see the solution of this y. Okay, solution of this y is either you can represent it in terms of sin x or in terms of cos x or any linear combination of this. Okay, so let me tell you in general that y can be, the solution of this is just a sin x, okay, plus b cos x. So this is your solution, or actually this is omega x, not only x, there is a constant term omega. So this can be written as a sin omega x plus b cos omega x. Okay, so y can be written like this, or if you want to write this y as f of x, then it can be write like this, a sin omega x plus b cos omega x, b cos omega x. Okay, omega x. So you can see this function f of x is represented by the function sine and cosine, and not only the solution of this differential equation, but there are many kinds of periodic functions that can be represented or can be expressed in terms of sine and cosine form, and that is, and if this can be written in terms of series, then this is called actually the Fourier series. So you know, if there are more terms, okay, instead of sine omega x and cos omega x, the solution may be this kinds of also. If you see in wave, then there is a superposition of many simple harmonic oscillations. In that case, there is not only one term sine omega x or cos omega x, you can see this kinds of function. Let me write down. So you can see this kinds of function also. That suppose f of x is the sine omega x plus sine 2 omega x, okay, plus sine 3 omega x. There are more harmonics, okay, 2 omega x. There may be exist more harmonics, 3 omega x dot dot. Okay, so these kinds of, and if you take the constant like a1, here a2, okay, here a3, this kinds of situation may be arise. Okay, plus you can get the cosine terms also like this, that is b1 cos x or cos omega x, if you want to write omega x, plus b2 cos 2 omega x dot dot. Okay, so this can be represented in this way also, and it is not necessary that it will be only the sine and cosine term. Any periodic function, if you add a constant, so it will also be periodic. It will also be periodic. So sometimes it can be represented like this. So in that case, you can write a constant here also, a0 by 2. Okay, and 2 is used here as for symmetry. You will understand later on why we use. So you can write instead of this constant a0 also, another constant, okay, like this, or you can divide it by 2. You can take the constant a0 or by a0 by 2. So this kinds of situation, and sometimes this omega can be represented by n also, so it will be just like this, it will be just like this. Okay, so this is the Fourier series, and this can be written sometimes like this, a0 by 2 plus summation n sin nx, so you don't use n, okay, sin x, sin 2x, this kinds of situation may be arise. Okay, so you can write sin nx plus bn cos nx, n is equal to 1 to infinity. Okay, so this is the Fourier series actually, that f of x is equal to this. So any function f of x which is obviously periodic function, and must obey the Dirichlet condition. I will discuss about this. What is Dirichlet condition? Okay, Dirichlet condition. So which follows Dirichlet condition, obviously be a periodic function, and any periodic function can be written in terms of sine and cosine. the series of sine, infinite series of sine and cosine, and this is known as the Fourier series. Okay, but why we need to write the function in terms of Fourier series or in terms of sine and cosine terms? One of the reason is that sine and cosine are the periodic function. Okay, so as sine and cosine are the periodic function, so it will be very effective if you, and this is the sine and cosine, the most simplest periodic function. So if you expressed any periodic function in terms of sine and cosine, then your analysis will be easy. That is one of the reason why we need to expand any function in terms of Fourier series, in terms of sine and cosine. Otherwise, there is another benefit also in power series. If you study about power series, then you know that in power series, the coefficient of the power of x, there need some higher order derivatives also, like f dash x, f double dash x, f triple dash x. If you know about Taylor series, then you see that the coefficient of x square, x cube, x to the power 4, there are some successive differentiation like f dash x, f double dash x, f triple dash x. So only those functions can be expanded in terms of power series which have the continuous derivatives. Okay, so the derivatives should be exist. The higher order derivatives should exist of this function. Only in that case you can expand a function in terms of Fourier series, in terms of power series. Okay, and the function should also should have to be continuous also. So you can only expand a function in terms of power series when the function is continuous function and the function should have the higher order derivative also. But sometimes we need a function and we have to express a function in terms of series, but the function may be of discontinuous function. Maybe its higher order function it does not exist. Maybe the function has a sharp corner. In that case also, sometimes in physics, we need to express the function in terms of sine and cosine or in terms of series. So the only way of doing this function, if you want to express that function in terms of series, you have to expand in Fourier series. Because you know, we will see later on in electronics, or you might have studied in your 10+2 level, that half-wave rectifier, okay, this kinds of periodic function will be there. This is discontinuous function, but this is a periodic function. Half-wave rectifier, you know. And another is, you will see there is something like this rectangular wave. You can see there is a sharp corner. This kinds of periodic function you will see in many branches of physics. Okay, or you can see sometimes this kinds of function also, the sawtooth wave function, this kinds of, okay, so this is triangular wave. So this kinds of periodic function you will see. Okay, and you cannot solve or you cannot expand this kinds of function in power series method. So the only way to expand the function is that Fourier series, that is in terms of sine and cosine. Okay, so any periodic function can be expanded. Maybe the function be discontinuous, maybe the function does not have the higher order derivative, but the function should have period. Okay, so functions should be periodic function. So f of x should be periodic function. This is very important, and I will tell you later on, not only condition that the function should have the periodic, but other than it should obey some conditions called Dirichlet's condition. I will tell you later on. And so the very initial requirement is that the function should have periodic function. Okay, so this is one of the mathematical tool for Fourier series, you know, that you should have some knowledge about periodic function, and I will discuss in the next class. Okay, and another thing that you know in your 10+2 level, that is the integration by parts. Okay, integration by parts. Okay, so this is also one of the mathematical tool, and another mathematical tool is the average value of a function. average value of a function So I will discuss about this mathematical tools little bit in the next class. Then I will move to this function, this Fourier series, how we can expand a periodic function in terms of Fourier series, and what will be the coefficient of a0, an and bn. What will be the expression of a0, an, bn? I'll discuss in the next class. Okay. After discussing these three mathematical tools that you need if you want to expand a periodic function in terms of Fourier series. Okay. Thank you.